Okay, so 3 large identical balloons are filled with 22.4 liter of gas at STP. That means that's a 1 mole. 22.4 liter is 1 mole. These gases are helium, hydrogen, and sulfur hexafluoride, SF6. What follows is a list of statements about 3 balloons. Comment on accuracy of the statement using specific detail to support your argument and comment. Okay. Hydrogen is the smallest particle. Yes. Balloon with the hydrogen will contain the largest number of moles. No. Okay, so this is false because and under the same pressure and temperature, the amount of moles should be the same if it has the same volume. Okay, so 1A is false. Okay, it has to do with Avogadro law. Gas molecule under the same temperature and pressure having same volume will have the same number of gas molecule. Okay, let's talk about B. Kinetic energy of gas molecule compare is as following. It is false. Kinetic energy is directly related to the temperature, and since it's the same temperature, it should be the same. Right? All gas molecule will have the same average kinetic energy. Right. Every kinetic energy is directly proportional to the directly proportional to the temperature. Okay, and then so same temperature, same kinetic energy. C. SFS will deviate the most from ideal gas behavior. Okay, take a look. This is true because if you look at it, we have He, which is noble gas with 4 gram over mole mass. H2 is a diatomic molecule, nonpolar too, with 2 gram per mole mass. When you look at SF6, is actually polar and it has higher mass compared to this. Larger, right? Or largest compared to He and H2, right? Gas molecule. Let's talk about D. D said one day fill the balloons. One day after filling the balloons, all 3 will have decreased size by the same amount. This is actually false. Okay. Because balloon decrease in size due to effusion. They're leaving out of balloons somehow. And the rate of effusions, right, is going to be different. Yes, they all have same kinetic energy, but they don't have the same speed. The speed is going to depend on both kinetic energy, which is temperature, and the size. So SF6 is actually going to diffuse the least. Hydrogen is going to diffuse the fastest, and so is the helium, right, compared to SF6. So no, balloon reduce size due to gas diffusing out of balloon. Even though all three gases have same average kinetic energy, they diffuse at different rate due to mass difference or different in molar mass. Okay, so yeah, heavier gas molecule will move slower. Alright, so it's happening. Number 2. So let's gotta go with the picture. Okay. Hydrochloric acid is being dropped into zincs. Let's see what happened. Some of the zinc placed in a reaction vessel, hydrochloric acid is added, and hydrogen gas is generated. So this is H2 is being generated and filled in here. Okay. When the reaction reaches a completion, the gas collection test tube is nearly full. The gas are allowed to sit for several minutes. The collection tubes was then adjusted so that the level of water in the tube was equal to the level of water outside the tube. Okay. The volume of the gas was then determined to be 47 milliliter. The temperature of the water is 22 degrees Celsius. Barometer pressures is this. This is the air pressure. Vapor pressure is this. Okay, we have a couple of things in there. The thing is you need to understand what they give you. Okay. First thing first, volume of the gas, right? In there, that's how much volume. So that's gonna convert into liter. So 0.047. Temperature, go ahead and convert it to Kelvin by adding 273. Notice that that's the temperature of water, but we can also say this is a temperature of gas because they are in contact with each other. If they're in contact, they're gonna share the same temperature. Now, if you look at the barometer pressure, it's tell you this, that's the air pressure, okay, which also happen to be pressure in here, right? That's the pressure of the container. What is this in here? And then if you get to vapor pressure of water, remember that's a vapor pressure. So you need to subtract that so that I can get the pressure of H2. Okay, so let's get started. A, calculate the number of mole hydrogen gas being produced. All right, so we need mole. Notice there's nothing in here that kind of tell you grams, so we can do gram to mole. That means we are doing PV equal to nRT. And also happen that this is gas, so we are definitely doing PV equal to nRT. So let's get started. Number 2. Okay. So PV equal to nRT. To find N, that's gonna to be PV over RT. Okay. So let's go ahead and solve this. PV, pressures of the H2. So we gotta find that first. Volume, we know that volume. We know the R, we know the T. So let's go. Let's do that first on the side. So to find the pressure of the N2, oh no, not N2, H2, you're gonna do P of the container, right? P of the container inside minus P of the H2O vapor. Okay, P of the container in this case is the same thing at atmospheric pressure, so using 745 minus the P of the water, 19.4. We're gonna do this math. Okay, let's see. I'm gonna do calculator, but notice that 745 minus 19.4, when I get 725.6, 725.6 mmHg. Okay, I'm gonna go ahead and convert that to ATM right away. Divided by 760, 0.955 ATM. Now that I have it, I can get started here. 0.955 ATM times the volume 0.047. Remember, this is liter. R 0.08206. Okay, this R unit ATM liter divided by mole Kelvin. Okay, temperature is in Kelvin, 22 plus 273. Go and solve that. That's gonna give me mole. Okay, so go ahead and time that by 0.07 divided by. So we're gonna get small 0.00185 mole of H2. Okay. Now let's talk back to here now. Explain why it was necessary to allow the gas to sit in a tube for several minutes before determining its volume. Okay. Why is it allowed the gas to sit in there? Because we want to make sure the gas in there has the same temperature as the water, so that we can tell the temperature of this gas. That's all we're saying. Okay. C. Explain why it was necessary to adjust the level of the tube so that water level inside and outside were the same. Okay. The reason we're adjusting the water level, notice that if the water level inside and outside the same, that means the air pushing from the outside is the same thing as the inside gas air pushing back the water out. Basically, I want you to think about the manometer question that you guys had the other day, where you kind of look like, oh wait, no, I draw it backward, but I draw it backward. So let me redraw this. So you have a circle and circles, and you have a tube going like this, right? So that the circles, the gas in there is gonna push, the outside is also gonna push, but you're gonna check this level, right? If this level is the same, then you saying that inside pushing is the same thing as outside pushing. Same here. So inside the tube here, the gas gonna push down. The outside air is also pushing down here, which make the water go up. So if the water level outside and water level inside are the same, that means we're saying that these two air are pushing at the same time. So meaning, because of that, I can use this number here, the barometric air pressure of the laboratory, right, which is the air pressure, 745 millimeter mercury is also 745 inside here. So that's why you have to adjust that level. Okay. D. Explain why the vapor pressure of water is given. Vapor pressure is basically talking about how much water vapor is in there. Okay. Without doing chemical reaction and other additional stuff, we cannot tell how much water vapor is in here. So that's why they need to give it to you. In fact, this vapor pressure of water is usually given to you in the lab by a table. So it has to do with the temperature. At certain temperature, you have certain percents of water are in the gas phase. Okay. All right.